So let's take a look. I think this iterate while one will be a little bit easier. So we've got a little test function here. And we've got iterate while in. So the first thing that we're going to need is a predicate function that takes a single argument. And we can just say something like and then we need a m of a. A here is a string, and getLine is an IO of string. So we should be able to just do getLine. And in this case, iterate while is going to return the final result. So here we can just do another put string line, and we can do something, and we can say like finished with input combined with a close. Dun, 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 dun. Oh, yes, of course. Thank you. Very good catch. Didn't quite work the way we expected it to. This is the problem with I/O. Let's take a look at the docs real quick. Until it fails. What we want is this one. No. Get my indentation correct. Now it should work. The world is sane again. We're all right. So these come in pretty handy. I take it back that they're just easy peasy, but I think that they're not too bad, and you can work through them, especially if you have some people around, like I do right now. And indeed, this is really what we're going to do here. So generate random is a IO of n. An IO of integer. And generate large prime is also an IO of integer, which means that iterate until can take is prime, which is just the pure prime number test that we established, plus generate random, and it will go ahead and do that until it finds one, and then it'll return it. So we can, with this manner, generate very large prime numbers very quickly.
Can you do the same here where you drop the arrow and the return?
Uh-huh.
Does that work?
Yeah, that should work just fine. Exact same thing. Functionally equivalent. And if we did want to use it somewhere else, do something with primes, and we needed two of them, we could say P1 P2 and then the last statement has to always be wrapped up in the IO monad. Now we've got a tuple of two of them. Still quite fast. Cool? Pretty straightforward. Not too crazy. Okay, so now that we've got our primes, we're going to need a few other mathy math things. And so we need, we actually ended up needing quite a bit more than I had in my slides, but let's check out mathy math. Okay, so we need a way to find the greatest common denominator, and this is an implementation of Euclid's little theorem that quickly gets us the greatest common denominator of a tuple of numbers. And so we can generate this, we can demonstrate this with so I'm like totally running out of space here. And there's a trick to making these go away, but I can't remember what it is, to customizing your GHCI experience. But so we can capture this in generate large prime, and capture Q and generate large prime, and then we can return P and Q. Takes a tuple. dang it. Take that, terminal. Return. No. How the mighty are fallen. P. Q. Ah! Okay. Nobody. Do. P. Q. And return GCD prime tuple. Okay, so this is what we would expect because these are two prime numbers. We also need to find the modular inverse, which we use the greatest common denominator function for. This is going to be part of our encryption algorithm. And we also needed power mod. And so power mod is the equivalent of doing, so power mod P, Q, R is the same as P to the power of Q mod R, except it runs very fast and it works on very large integers. And the nice thing about this is I actually was having trouble getting, so this is the package that is like your best friend for any of this crypto stuff, math.number theory. And I was having trouble getting this version of it to build in my system. And the beautiful thing about Haskell is that you can almost always just jump over to the source, copy it directly into your project, and build it, and you're good to go. And so if you're ever into a situation where you just need like a function or two from a package and you're having issues reconciling it with your build system, that's a handy trick to remember. You can always just copy just what you need. Over. So that is really invert mod and belower are all from the math.number theory package. So thanks, math.number theorists. All right, so we talked a little bit about this, about little for the monadic computation. So let's talk a little bit now about what we're going to be doing with these public and private keys. So we create two distinct, very large prime numbers, P and Q. We multiply them together, and we get a number n. Then we need to find the number e, which is relatively prime to p minus 1 times q minus 1. Then we have to calculate the modular inverse of e and store it in D. And then that is going to give us the ability to run this encryption, which is where in order to encrypt, we just take our message and we take that to the power of e mod n to encrypt it. And then to decrypt it, we just take the same thing and we take it to the power of d mod n. And so then in this manner, e and n are the public key, and d and n together are the private key. And e, n, and d are all generated from this. Very large numbers p and q, multiply them, you get n. Then you create a random number e, which is relatively prime to it, and then the modular inverse of e is d. So this is what we're going to do. First, we generate the two large primes randomly, and we make sure they're not equal to each other. Then we multiply p and q to get n. Then we're going to generate random numbers until we find one, again, that is relatively prime to p minus 1 times q minus 1. And then we're going to calculate d, which is the modular inverse of e. And then the public key is just going to be a tuple of n and e. And the private key is just going to be a tuple of n and d. And we're going to write them to a file. Ready to check it out? Okay, so generate large prime tuple. This is really similar to what we had before, except we just return the tuple as is. Generate key files. We get the key size, and then each of these are essentially just imperative steps that we walk down. So we use our good friend iterate until again. And what we want to do is we need to make sure that the prime numbers that we generate are not equal to each other. If they're equal to each other, then we don't have 2. We have 1. It's not going to work. So then we do some non-monadic computation here. So we just multiply p times q. Now we need to find the greatest common denominator of p minus 1 times q minus 1. And so in order to do this, we generate another random number, which gets passed into this anonymous function. And then this gets evaluated each time until it returns 1, and then we capture the e. And that's what we mean by relatively prime. So that means that the number that we find when run with our greatest common denominator, with it and p minus 1, q minus 1, it will have no other factors except itself and 1, relatively prime. So then we need to find the modular inverse of that number and the product of p minus 1 and q minus 1. From there, now we've got everything that we need. Our public key is n and e in a tuple, and our private key is n and d in the tuple. And so then we use the write file action to write out the public key and the private key. And just to prove that I'm not faking it. Oh no. Oh yeah, I didn't finish the thing. So there we go. Pretty fast. You know what? About as fast as C running with OpenSSH. Obviously, this is a naive implementation, right? So C is doing some stuff to really make sure that the numbers generated are secure. But now we've got a private key with the number of bits and, or the key length rather, in this case, and our tuple, and there's one problem with this. Can anybody spot the bug in this mass of numbers? I think it's in both of them. Okay, actually it's not in both of them. It's just in the other one. Yep, the other one had just. So, good eye. Okay, so let's fix this bug together. We don't want to return a tuple of an integer and a just integer. We want to return two integers. So where is that? Who can spot where that's happening? I believe so. So find mod inverse comes from mathymath, so let's import mathymath and do type a to maybe a. So how can we fix that here?
What should happen if it returns nothing? Should we try again or generate new numbers?
Yeah, I think we should probably start over. I think really the only two things we could do would either be error out explicitly or to start over. Maybe let's start with erroring out because that'll be a little bit easier. But, and then we can try. So we talked about yesterday a little bit about what the strategies are. So when we have something that's wrapped up in a monad and we want to use the value, what is the Haskell technique that we use to get it out of the monad? Yeah, we got a pattern match on the data constructors. Let's see what we could do. Let's pull this out and let's for now we can just write a function that's just maybe mod unwrap maybe mod just a. So now always remember with the pattern matching, you gotta wrap it in parentheses so that Haskell knows that you're not trying to pass two arguments to a function. Okay, let's see if that works. D is in the private key, right? That one looks good. Now it looks good. So can we do this?
I mean, we can call unwrap maybe mod for it and run like recursively. Is it possible?
Say again?
If it's nothing, we again do generic. Oh wait, just I in the moment process it.
So first of all, somebody tell me why this is wrong.
Don't you cause infinite recursion?
Well,
Because
You're calling unwrap maybe mod back down in.
because the types don't match, right? Don't match.
it's the types that don't match. We're actually okay with the infinite recursion because if it got into an error state forever, if it runs it again, it would get 2 more prime numbers, and then if it got into an error state again, we'd be fine with that loop. But the issue is that unwrap maybe mod is going to take a type of just A and return an A, and unwrap maybe mod nothing is going to generate key files, which is itself I believe, an IO of unit. And so we're not going to be able to do that. So in order to, let's verify that real quick. Yeah. So this big type error is just saying, hold your horses. Can't do that. But
What do we, yeah, cannot do this in this function. We need to change it out.
I can't quite, I'm getting on a little bit of a rabbit hole but here, in fact, even we can, and I'm totally forgetting my case syntax. Just C. Okay.
Can I just like that actually the next line on the same indentation and another pattern? No.
Yeah. Yeah, it can be on the same line too. I just was blanking on it. Okay, if this This is going to get us into a little bit of trouble still, but getting closer to we still have so getting pretty close. I don't want to get too far down the rabbit hole, but so I'm going to go back to where we were before, but some of those other control structures could help us too. So instead of trying to pattern match on the instead of trying to pattern match it on there, some of the iterate while maybes would help as well better from the control.monad.loops package. Okay, so now that we've got our keys, we need to start working on actually doing some encoding. So what we're going to do is that we need to convert multiple characters into a single large integer block. And so if we take a 66 character symbol set of all the capital characters letters, all the lowercase character letters, and 1 through 9 combined with 0, a space, exclamation point, question mark, and period, then the formula that we need to pay attention to is that 2 to the power of the key size must be greater than the symbol set size to the power of the block size. And so in our case, it's going to be 169 because we're using 1024 for our key size, and that is less than 66 to the 170th, but it is greater than 66 to the 169th power. And so to create a block, we're going to multiply the symbol set index of the character by the symbol set size raised by larger and larger powers, and then sum up all the numbers. So we're going to need a map of symbols and indices, and then we're going to do something like the following. So given Because what we're trying to accomplish here is we need to take our characters into something that we can plug into that encryption algorithm. We got to be able to take them to the power of, do the power mod thing on them. And if they're characters, then that doesn't really help us that much. And we don't want to do that math for every single one of our characters as well, because it's, first off, it would introduce a vulnerability, because if we encode every character the same way, then no matter how secure it is, somebody can run a letter frequency analysis on our message and decrypt it. So even if it takes millions of years for us to crunch those numbers, they can just be like, well, there's way more of this 30-digit prime number than there are of this 30-digit prime number, therefore it's probably an E. I'm going to start moving down the line. This is how this. So let's say that we have the, like a message A. Oh, no. So we're going to have a map that we build up that has keys, which are going to be characters, and values, which are going to be indices. So A is going to be 0, B is going to be 1, and we're going to match up our string with indices. So A is going to turn into 0, A, B, C, D, A, B, C, D, E, F, G, H, I, J, K, L, M, 18. Maybe not exactly. Okay. And so now what we're going to do is we're going to take the first one, and we are going to go, so this is going to be 2 to the power of key size. No, sorry. It's going to be that's not quite right. I'm going to bring up the actual math so that we can see it. Yeah, that's right. So, it's going to be the set index of the character, so which in this case is A, and then we are going to multiply it by the length of our map to the power of the index that it's in the string. So A will be 0 times 66 to the 0th. And then M then is going to be 18 times 66 to the first power, and then we will have 20 times 66 to the second, plus 19 times 66th to the third, plus 0 times 66 to the fourth, plus 4 times 66 to the 5th. And we're going to keep doing this for our block size, which is going to be 169 characters. And so at the end, for every 169 characters, we're going to have one integer, which is the sum of all of these computations running together. So let's take a look at the Haskell. So anytime you see we're taking something that is foldable and bringing it down into a sum, fold is your best friend. And so here, block size is going to be the number of characters. And then chunk is going to be the characters that we're actually closing over. And this whole thing is going to return a tuple, and we're only interested in the first one. And the reason it takes a tuple is because the recursion that we're doing needs to keep track of two things. One is the sum that we're returning at the end, but the other is the incrementing powers that go through each time. And so n is the result that we're going to end up with, and then p is the exponentiation that we're going to be doing to 66. And so the first thing that we do is that we look up the character inside of our symbol map to get the index, because we need the index for this first number. And then we go ahead and we take n, which is going to be the sum of everything that's occurred before, and we're going to add it to I, the index, multiplied by the map size of symbol map raised to the power of p modulated by the block size. And so this is like a little bit more complicated than just taking it 0, 1, 2, 3, 4, 5, because we need the block size to be dynamic, and we want to make sure that we don't run into any issues there. And then each time we just increment the power p. And if we ever get into a case where we can't look up the symbol, there's really nothing that we can do to recover from it. And so we just say, sorry, that was an unsupported symbol, and we show what the symbol was. Now, we're going to need to make sure that we don't do that to just one block, right? We're going to have to do it to many, many blocks. And so what we do here is we encode the blocks by taking in the message and the block size, and then we map encode block with the block size passed to it. And by passing it a single argument, it's curried. So we get a function that takes a chunk back and then operates on the chunk, which is exactly what we need for our mapping function. And we map that mapping function over chunks of with block size and message. And one thing that I wanted to point out for this is that it's a very similar operation to what we're doing with the transposition cipher. And the improvement of it is that the transposition cipher still maps a single letter to another letter. But this takes that same idea of scrambling it via chunks, and instead of rearranging them, it folds them into a single value with a deterministic computation that can be easily reversed. And with that, this is a good spot to take a little break before we continue on. So let's go ahead and do that, and then we can come back up to encryption and also decoding the blocks. So I would say that this operation here, the encoding the block, is not strictly encryption, right? Because this is still you know, if we pass this out, anyone who understood how the code was being written could easily reverse engineer it, right?